So next comes another innovation that it's actually bringing up what Vignesh talked about, that there are some other constraints in our problem. What are the other constraints? We want our scheme to be consistent, that is increasing delta x should decrease the error in the Taylor. So in addition, scheme should be consistent, that is error should decrease with delta x. So we saw that the numerical schemes that we have looked at till now, the second order accurate has got delta x to the power 2 in the error. The fourth order is delta x to the power 4. And the 7-point stencil, which is what we are going to look at for example. So 7-point stencil full Taylor accuracy implies order delta x to the power 6. It's a sixth order accurate scheme. Okay. And you can quickly code that up to see that it is indeed better than the fourth order accurate. The wave number also is hugging that 45° line for a larger range of wave numbers. So Tam's idea was seek only partial Taylor accuracy. If you use the full Taylor accuracy, then we will already get the answer for what should be the A's, A0, A1, A2, all are already known. We already saw that, and that is also part of your exercise for your ungraded next homework. If we already have that, then there is no further degrees of freedom for optimization. All of these are already known. So how can I minimize this? How can I further change this? I am already constrained to a particular behavior of my scheme. So what he proposed is that I will reduce expected Taylor accuracy by 1. So now you would know this. So for a 3-point stencil, we have got n is equal to 1, that is one stencil point on either side of the central point, and the order of accuracy there was 2. N is equal to 2 gives me a 5-point stencil, order of accuracy is 4. 7-point stencil gives me 6th order accurate. So if I were to decrease the order of accuracy by 1, what should I do? Where should I take it to? 5? 5 will make it an unbalanced scheme. You can try it out. We have seen that, and in fact you can see that here. That's why we have got these even orders of accuracy. So you have to reduce actually, for a central difference scheme you have to reduce it by, so that is for 7-point. Now instead of requiring n equal to 6, that is 6th order accuracy, you settle for n is equal to 4. So what that means is that if we have 3 coefficients unknown, remember that we are with a 7-point stencil, because we have got this symmetry, so A minus j is equal to minus aj, that means for 7-point stencil, A1, A2 and A3 are the unknowns. Okay. The minus are obtained from this, and A0 is 0. So these are 3 unknowns, and in the full Taylor accuracy we devise 3 equations to get those 3 unknowns. So those 3 equations give me the 6th order Taylor accuracy. So I get to set the multiplier of the final term to 0, and then anything beyond I can't deal with it because I don't have the bandwidth, I don't have the degrees of freedom to deal with it. So when you now want to reduce the Taylor accuracy, you have to take, so this means that there are 3 equations. So for 7 point, if you have 2 order less of accuracy, mean you look at only 2 equations. So you've got an underdefined system. So you'll have, say, a system of this form. So A11, A12, A13, A1, A2, A3 is equal to some B1, B2. So you've got 2 equations in the 3 unknowns. So we'll formulate this maybe in next class to come up with a relation between the 3 unknowns. So we'll like to write this as A2 is some, say, C 0 plus C21 A1, and A3 is equal to C, sorry, C20, C30 plus C31 A1. So I want to write using this solution because it's an underdetermined system. So I will write A2 in terms of A1, A3 in terms of A1. So A1 is my only unknown. After solving these 2 equations, A1 is the only unknown. That then becomes my only degree of freedom here. So I will write that after I have satisfied the consistency requirement to a lesser degree than is possible in Taylor, full order Taylor, I will now be left with only 1 degree of freedom that I can then try to minimize. So once you do that, you will get a value of A1, which is going to minimize this error. Symmetry is already enforced. So because I am enforcing symmetry condition, I end up with a 4th order accurate scheme, not a 5th order. So 5th order would have gotten me a asymmetric stencil, which is again bad for decay and growth of the solution. So we have seen that for 7-point stencil, we have got 6th order accuracy, and for a 5-point scheme, we have got 4th order accuracy. So we'll see, if you do the all the permutations, you'll see that if you suppose you want to keep 1 degree of freedom at least for yourself for the optimization problem that you will now try to minimize to get to set this to 0, then you just want 1 degree, at least 1 degree of freedom. So that means that if you treat the 7 different coefficients, then you can set 6 coefficients in terms of the 7th one, and then choose to minimize this with respect to the unknown thing. But that will end up with an asymmetric stencil. So what you do instead is you use the symmetry still, the symmetry property of your stencil is still preserved, that is A minus J equal to AJ. So this you still preserve so that the wave numbers do not decay or grow. So this is preserving your it's not allowing solutions to grow or decay in space. If you want to preserve that, then you end up with a 5th order accurate scheme now. Okay. So instead of 7 point giving you 3rd order, 6th order accurate, you end up with a 5th order, 4th order accurate scheme. So for that again, you will, so we'll again do this in next class specifically for the 7-point stencil, and we'll see that we'll end up with, we'll require 2 equations. If you want 4th order accuracy, you'll require 2 equations, and they will be formulated in this form. So you can then again, so basically you can write this as A12, A13, A22, A23 into A2, A3, B1 minus A11, A1, B2 minus A21, A1. So this is a Ax equal to B thing, which you can invert to get A2 and A3 in terms of a constant and A1. So this is what I have written. Okay. Solution of that will give you this thing. where you now have only one unknown, A1. And if you get that, then you also get the A23 out of it. So then you repose this scheme in terms of the only unknown A1. You substitute for A23 in terms of A1. So everything is now in terms of A1. So your cost function is in terms of A1, and you get to minimize that. So we get to look at it with the right eyes. If you were not looking at it with the wave number perspective, you would have missed that you can do this thing and not be stuck in the Taylor approach to evaluating schemes only. So the Taylor approach is a very general scheme, and it is good. That's why we are retaining parts of it, a large part of it. We are determining two coefficients from that, but it is not the only thing that matters in computational error acoustics.